theorem 5 is the Schwartz inequality. We saw the Schwartz inequality in one of the previous videos and we will prove it over here right now. So theorem 5 is the Schwartz inequality. The Schwartz inequality states the following. If we have two vectors v and w, so given any two vectors v and w, the magnitude of their inner product would be less than or equal to the product of their individual magnitudes. So let us now prove this inequality. Let us construct a new vector z. So v and w are already given to us. Let us construct a vector z from this v and w by the following construction. So this might look like a strange construction right now, but this construction would be very helpful in proving this inequality. So what do we have over here? We have taken the vector v and subtracted some coefficient times w. So this coefficient over here is basically the inner product of v and w scaled by the magnitude squared of w. So this is the z, how we construct z. Now let us find the magnitude of z, or rather the inner product of z with itself. So let us find out this inner product. Let us now just expand this and write out all the terms explicitly. So just so that we do not get confused, let me write it down step by step. So I'm just expanding it. So we have explicitly now expanded it and written down the 4 terms. So let us simplify it further. Sorry, I've made a mistake over here. This is power 4, not just squared, because we had mod w squared here and mod w squared here. So that would give us mod w to the power 4. And also, I've written down this term a little bit incorrectly. We have so basically we had this inner product of w and v, and since it is in the bra format, so we have this complex conjugate of it over here. Then we have this inner product of w and v, and then inner product of w and w. So this is the correct term. I had written it down incorrectly little bit a few minutes ago. So now let us simplify some things. This is nothing but mod w squared by definition. So we have mod w squared, and we have power 4 in the denominator. So certain powers will cancel. So these two terms right here will cancel out. They are identical. So we get the following. Now, from the axioms of inner product, we have that the inner product of a vector with itself will always be greater than equal to 0. and this is written down as following mod z squared. So this will always be greater than equal to 0. So equality is only for the null vector. So mod square of the null vector will be equal to 0. For all other vectors, the mod squared or the inner product with itself is going to be positive. So this is an axiom. Using this axiom, we see that this inner product will be greater than equal to 0. So this term out here would be greater than equal to 0. Let us write it down again. So using this axiom, we have the following. Rearranging the above inequality, we get the following. Now this is nothing but mod v squared. So we get again rearranging a few terms. We get this. Now this by antilinearity is basically equal to the complex conjugate of this. This comes from the axioms. This axiom being skew symmetry. So this comes from skew symmetry. So that means we get and this is nothing but, by definition, this is mod of the inner product squared, because this inner product over here will be some complex number, and a complex number times its complex conjugate is nothing but the magnitude squared or the mod squared by definition. So now taking square root on both sides, we get the desired Schwarz inequality. We could rearrange it in the conventional format by writing the following. So this proves our Schwarz inequality. So note that it was important to start with such a construction for a new vector z from the given vectors v and w. This construction was really helpful in proving this inequality, even though at first sight this construction might look a bit complicated, it might look something which is not intuitive at all, but this construction helps us in proving the Schwarz inequality that we wanted to show. So Schwarz inequality, if we restate it once again, it basically says that the magnitude of the inner product of two vectors would be less than or equal to the product of their individual magnitudes.